Hello, I'm Katie Steckles.
And I'm Peter Rowlett. And hi Katie, what's today's mathematical object?
Today's mathematical object is the Joukowsky aerofoil,
Wow.
which is a very specific object. So this is a thing which I basically came across in the course of teaching a series of lectures about complex numbers. So we're talking about complex functions and complex transformations. And this kind of popped up as an example, because obviously everyone needs there to be examples of real-world applications of everything in order to use to learn them and be motivated. But actually, I thought this was quite a really neat little example, and it's kind of almost a perfect real-world application because it's like a motivation for using the maths, but also a really inspirational breakthrough and a great story. So I've got a very sketchy idea of how all of this stuff works, but basically we were looking at complex functions. So for a bit of context, complex numbers kind of live in this two-dimensional space. If you haven't encountered complex numbers before, don't worry too much, they're just numbers, but they live in two-dimensional space. And basically, mapping complex functions is quite complicated because if your numbers are one-dimensional, you can draw a function. You can have one of the numbers along one axis and then the result of applying a function along the other axis, and you can plot what that looks like. And you can see, if I put this in, what do I get out? If the inputs and outputs to your function are both two-dimensional, you can't really do that because
you end up with a four-dimensional.
Yeah, you just have a four-dimensional graph. Yeah, of course, but you can't really draw that on a piece of paper. So it's really quite hard to see what the effect of applying the function is. And a lot of the time, what people do to try and visualize complex functions is they'll take a simple shape like a square, a rectangle, or a circle, and take the image of that under the function, because the function literally just says, "Okay, give me 2 coordinates. I'll give you 2 coordinates back." So if you put a square in there, you'll get, a slightly wonky shape, but it's got 4 sides and the corners join up, but it might not necessarily be a square. And for a lot of, I'm going to say, well-behaved complex functions, this is a word that mathematicians use to mean a set of extremely specific properties. Yes. But for particular well-behaved sets of functions, which luckily include most of the regular things you'll come across, so things like, so in complex numbers, the variable is almost always z. So, f of z is z squared or z cubed plus 4z. So anything that's like a nice simple polynomial, and also including 1 over z and, z squared over 2z and kind of linear combinations of things. Anything that's simple enough, anything you wouldn't feel bad about having to differentiate it, will give you a particular property called conformal. So conformal mapping is one which sort of is straightforward enough that this works. And the result is that basically it keeps angles the same. So if you've got a rectangle and you map it under a conformal map, the thing that you get will have 4 right-angle corners. It will absolutely not be a rectangle, but it might be some kind of like a lens shape, like a thing with a point at the top and bottom with a nice right-angle corner, or it might be a thing with 4 of those. Like if it's got 2, it's because the two of the corners map on top of each other. Right. Or you'll have something that's pointy or has a big curve gouged out of it or something. But all of the corners, all the points where the lines meet, tangents at that point will meet at 90 degrees. So the corners are somehow preserved by this map, which is nice and it's a useful property. But it sort of, it feels like teaching about this, like, that's nice. That's it's a good property for a map to have, and everyone's like, yeah, okay.
Good bit of pure maths, well done.
Yeah. So we kind of wanted an example to motivate this, and the notes that I was teaching from, I inherited from the person who taught before me, but I found this incredible example. So Joukowsky was a mathematician in the sort of early 1900s, published in 1910, discovered a particular function. So the function is z plus 1 over z. Okay. Nice little function. If you put in z, it gives you z plus 1 over z. And if you take the image of a circle under this transformation, it gives you an aerofoil. Okay. So this is the cross-section of a plane wing, right? If you're trying to imagine this, it's sort of a big rounded bit at one end and it goes to a thin point at the other end. And I guess, because, these complex functions mess things around and they map stuff, you can expect it will give you some kind of weird shape. But actually, this is significantly more useful than it might initially seem, because this function is conformal, right? It's a nice simple function, I realise that I've said that the corners are preserved and there aren't any corners on a circle, and there very much is a corner on an aerofoil, and I can see it in your face that you can ask me this question. It's not necessarily conformal everywhere because there's 1 over z in it, so there'll be like a single point where it doesn't necessarily work. Okay. But you get an aerofoil. But the thing about this is, everywhere except on this circle, it also maps the whole of the rest of the space as well, and we're just using the circle as a way to sort of see a slice of what the map does. So if, for instance, you put a circular plane wing in, what's it called, a wind tunnel, where you've got air moving over it, a circular shape is simple enough mathematically that you can actually correctly plot what happens to the air. So if you're imagining like a vector field, we did a podcast about a hairy ball, right?
Yeah.
We've talked about vector fields. So if you imagine the kind of little arrows, the invisible magical arrows representing the flow of air around this circle, the way that they behave when they go over the circle, I'm genuinely miming it with my hands now, but you're all imagining it as well. But it kind of splits around the cylinder and comes back together at the other side. And that pattern of airflow is well known, well understood, including in 1910, before anyone's got, GeoGebra or MATLAB or any way to plot this as a diagram. But this is something that you can, put some smoke in the air and watch it happening, so it's understood. But because this map is well behaved and conformal, it will also map the vector field in a consistent way to the aerofoil shape. So actually understanding and knowing the exact mathematical properties of that vector field mean that you can actually say what's happening around this aerofoil. And for some reason, people seem really interested in how air moves over a plane wing. It seems to be important for various technical reasons. So actually what this meant was that as early as 1910, Joukowsky was able to tell people what the vector field around a plane wings looks like mathematically, because you can map, it's a function, so you can take the description of it mathematically and take the image of that. And it corresponded to what they were seeing in the wind tunnels. So actually the maths is made a huge amount easier. You don't have computers, you don't have any way to sort of crunch all this stuff, but you do now have a very simple mathematical description.
Because you can whip something around a circle, but the actual aerofoil shape is so complicated
that
it'd be really hard to do directly.
Yeah, and what's nice about it is that you can modify this function. So z plus 1 over z is a simple one, but you can stick some coefficients in there. You could have numbers in various different bits of the equation, which will affect how thick the aerofoil is, how thin the point is, how wide it is, all of these kinds of things. So you can modify it slightly. And actually since then there's been other transforms which have slightly different aerofoils. There's a whole different class of complex functions which will transform a circle into various different kinds of aerofoil shapes, and some of them are actually better for real plane wings, but this was like the first example of this, and I just find that really lovely that this kind of random piece of complex function studying came up with actually a really practical, nice way to understand something mathematically when that wasn't even something that people could do yet. And obviously as years have gone on, people have refined this, and they use computers now for
actually
this stuff.
started building aeroplanes.
Yeah, probably, yeah. Well, that's the thing, yeah. A lot of modern aeroplane development since this time. Yeah. This is like very borderline early days of aeroplanes, I guess. But yeah,
complex numbers sort of just come out of this weird quirk of sometimes when you're rearranging cubics, the square roots of negative numbers appear. I wonder what happens if we play with them for a while.
Yeah.
And then it has all these fantastic
and I guess notionally a lot of this stuff could have happened if you were just thinking about two-dimensional coordinates as well. But the definition of this function in complex is just z plus 1 over z.
Really
It's
simple.
such a simple idea. But yeah, generalises to lots of different possible aerofoil shapes, and has inspired future transforms that give you different things as well. And I guess, I'm not sure to what extent it is used today, but I imagine the fact that this exists has kind of given, because my understanding is that fluid dynamics is really hard, so I imagine any shortcut you can give yourself is probably quite a useful thing.
Yeah, and this is one of the things that complex numbers do, isn't it? Is the fact that it's encoding two different things at once means that you can do a bunch of things more simply than you would otherwise. And this is how it's used in electricity as well, is that it's able to encode two different things, and you can do one operation on those two different things at the same time.
Yeah.
And here, that's your two coordinates in space.
Yeah.
But
yeah. That's the object. It's the Joukowsky aerofoil, and Joukowsky is spelt very differently depending on whether it's the Americanized spelling or the original spelling. Because Joukowsky was Russian, so obviously the original spelling was in Cyrillic, but Americans seem to spell it with a J, which is probably not original. That's the name of the thing.
Okay. Okay, so we're both on Twitter and Mastodon. I'm at Peter Rowlett.
And I'm at Steckles, and the podcast itself is on Twitter at MathsObjects.
We both blog at a website called aperiodical.com, where you can find more episodes of this podcast.
And if you have any thoughts or comments or suggestions for other types of aerofoil that we could talk about, please drop us an email, objects@aperiodical.com.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.